Good evening here. I'm going to do a special bonus supplement lecture here to help clear up some of the confusion, or rather questions you might have about how these non-blocking and blocking assignments work together. Hope this benefits you. Give me some feedback. Tell me if you'd like me to do some more, but hopefully this helps my students. Okay, so what we've got here is we've got ourselves a test bench. Now, this test bench is new. I've added this. What you remember from the slides in class is your toggle flip-flop. This is a simple design in which what we do is at every positive edge of the clock, we check to see if toggle has occurred. If toggle has occurred, we just invert the value, the currently valued, the stored flop value. We just basically negate it. And so what happens is we basically, when you hit a button, the light goes on. When you hit a button, the light goes off. And you can go on and off, on and off. It's kind of a nice logic feature that you can use inside your state machines or handling control logic. So now the question is, you see a lot of this non-blocking and blocking stuff happening together. And so the question we have to ask ourselves is, how does this all work together? Well, let's take a look at this, and let's simulate this mentally from time zero. What we're going to do here is we're going to kind of come up with a set of rules here to help us handle this. We're going to say that this initial forever is a process, okay? And we're going to basically call this process 1, okay? We'll call this initial begin process 2. Whoops, gotta copy it. And we'll call this always block process 3. Okay, so what happens is our simulator is sensitive based on the resolution, that the time scale specified in our design. So what happens is our time scale could be 1 nanosecond by 1 nanosecond, or 10 nanoseconds by 10 nanoseconds. What that means is it'll basically allow the simulator to increment in 1 nanosecond increments, meaning it'll model the discrete event, or rather the circuit behavior, in 1 nanosecond increments. And we have another definition, and so let's just go ahead and add that. Oh, I can't. But we have another definition that allows us to define the delay, what those units mean. So let's just assume, for the sake of this example, that we are using a time scale of 1 nanosecond over 1 nanosecond. So we're going to say that the delays specified are in nanosecond increments, so 5 nanoseconds and 30 nanoseconds, and we're going to say that our simulator clicks along at 1 nanosecond intervals, meaning every event that occurs can only happen on a 1 nanosecond boundary. Okay, so simple enough. So at time 0, we go ahead, and time 0 we actually have to look at our initial blocks, because our initial blocks start at time 0. So initial, well, this says forever pound 10. Okay, so immediately we know that this assignment will not actually occur until 10 nanoseconds later. So this will take the inverted value of clock, not clock. So we can actually technically ignore that statement until 10 nanoseconds has actually passed. And we're going to do that to keep things simple. So what I'm going to do here is I'm going to start creating some time for us to, I'm going to create some reference points so we can kind of keep track of how the simulator is progressing. So we have 0 nanoseconds, 5 nanoseconds, 10 nanoseconds. Okay, so we've got through this, and we said it's not going to do anything until here. So let's go to our next initial block, which also starts at time 0. So what we have here is we see that toggle goes to 0. Okay, so toggle, and so let's just call it toggle. Toggle will go to 0, it'll be the first signal, but it actually doesn't go to 0 right away. What happens is our simulator says capture the right hand side of this. So we have something that happens. What we do is at time 0 we say grab the right hand side, and that'll be what? Should be 0, okay? So at 0 nanoseconds, the right hand side is 0. We haven't, now remember again, our steps for handling a simulator are as follows. Okay. In phase 1, we basically assign blocking and capture the right hand side of non-blocking. So what's going to happen here is step 1, we need to do that. Okay, once we've done everything there, we then assign non-blocking. Step 3, and this is actually going to get more complex as we go on in the course, but step 3, what we're going to do is we're going to see if any events occurred from step 2 and step 1. Okay, if so, we're going to loop back around and we're going to... Whoops. Ah, come on. If so, go to step 1. And this happens, okay. Now, this happens continuously until everything at that current time step has been solved. Okay, so what's going to happen here is, so toggle, we grab the right-hand side. Reset, we grab the right-hand side. And it's currently 1, okay? So what happens then is clock, we also grab the right-hand side. Okay? So what happens is, now we've come down to this step here, pound 5. Well, we can't do anything in the current time slice because this assignment cannot occur until 5 nanoseconds later. So at this point, our process, we've done all we can for step 1. So now we have to go, this process waits. Now we go to process 3, and we ask ourselves, has a positive edge of a clock occurred or a neg edge reset? The answer is actually no, because we haven't assigned any of these yet, right? We haven't had a pause edge event because we haven't assigned the clock yet. So we can't actually wake up process 3. So what's going to happen here is now we're going to go to step 2. We're going to assign the non-blocking. And so what that means is we're going to basically, at time 0, this is going to go to a 1. And there we go. Reset's going to go to a 1. Okay. And toggle is going to go to a 0. So the way that works here is now we've got initial values. So the question here, though, is from that, did anything wake up? I'm going to put these over because I can use them later. Did anything wake up from clock going from 0 to 1? And let's go ahead and let's give this direction here. Let's just say arrows. Oh, that's too big. Okay. Let's see, line weight. Okay, well, we're not going to give this arrows. Sorry. Okay. So we have this going from 0 to 1. That is called a pause edge clock. So what happens is, upon the assignment of all those, we go to see if any events occurred. Yes, an event did occur. Did an event occur here? No. Did an event occur here? No. We're not sensitive to anything. So an event occurred here at pause edge clock. And so what happens is we wake up this process. And this process then says, okay, are we in reset? No, reset's 1. Okay, so we say, else if toggle. Well, toggle's actually not high at this point. So what happens is sig out basically gets the inverted value of sig out. So my question is, what's sig out at this point? Well, you should be thinking it's x. Sig out is x. And so what's going to happen is sig out is going to remain x because the inverted value of an x is still an x. So what's going to happen here is we would capture the right hand side, we would see X, we would then go ahead and assign it, and we would get X again, and then we would see if anything woke up. Nothing woke up. Okay, so we are now done with 0 nanoseconds. We have now officially completed the 0 nanosecond simulation cycle. Okay, so the question is, when does the simulator wake up again? Okay, well, since a discrete event simulator only actually actuates on events, we will actually wake up on the next scheduled event or the next scheduled assignment. Well, if you remember, the closest next scheduled assignment was pound 5 nanoseconds, or 5 nanoseconds later. So 5 nanoseconds later, we go ahead and we assign reset to 0. Well, actually, it's not quite that simple, right? So what happens is we capture the right-hand side of reset, okay, and it'll be, we're saying it, we want it to be 0. Okay, so during this time slice, we capture the right-hand side of reset. It's 0. Does anybody else wake up? Well, no, because there's no event happening here yet, and this is not going to happen for 10 nanoseconds. So, what happens? Well, we basically go ahead and we assign the right-hand side. We assign reset to 0. So what happens is, whoops, 5 nanoseconds later, reset goes to 0. Okay, so it went from X to 1 to 0. Okay, so toggle went to 0, and so there we go. Sig out was 0 until here. Let's see, clock went to 1. So now we're just completing the waveform. We're basically drawing it out. So, okay, so now we've assigned the right-hand side of that. And now we got to ask ourselves, did any events occur? Well, actually, yes. Reset went from 1 to 0, okay? Now that reset went from 1 to 0, we actually wake up process 3. And process 3 says, okay, well, if reset sets sig out to 0, well, what do you know? Sig out goes to 0. Okay, so right there, sig out goes to 0. And again, we take the right-hand side. We then go ahead and see if there's any blocking assignments remaining. Then we come back and we basically assign it. Now, since there's the next assignment to occur in process 2 is going to be 30 nanoseconds later, we can actually go ahead and just extend this out for 30 nanoseconds because we know it's not going to change. We know that this will not be assigned for 30 more nanoseconds, so we can just assign reset out that far. Okay, and we know this will not wake up until 30 nanoseconds later. So 15 nanoseconds. Let's just go ahead and come up with some arbitrary scheme here. Okay. And so we get the point that basically at 25 nanoseconds, or sorry, at 30 nanoseconds, we then are going to evaluate this. Well, we can actually ignore this right now because we're now stuck at 10 nanoseconds, right? We finished this, and remember, the next event scheduled to occur is actually at 10 nanoseconds. And this says to go ahead and invert the clock. So what it's doing here, and look at this is a blocking statement. So what happens is, this actually occurs immediately. Assign blocking, okay? Now, this went active low. I'm sorry, this actually happens here, my bad. Okay, so this goes low. Okay, and it happens immediately, and we schedule another event for 10 nanoseconds later. So we know that this assignment will occur again 10 nanoseconds later. So we can just basically draw that out. We can say, okay, fine. We don't need to do anything for 10 nanoseconds. And let's just go ahead and clean this up. Align. Whoops. Auto space. Position. Space shapes, whoops. Align bottom. Okay, fine. Let's do it. We're gonna cheat. We're gonna actually see what this, so we can just quickly clean this up. Okay. So what's going on here is, remember, this isn't going to happen until 20 nanoseconds later. This isn't going to happen until, this happened at 10 nanoseconds. So, that's 5 nanoseconds. That looks good. That's 5 nanoseconds. Sig out went low when? It went low at the reset. So we're still good. Everything looks good. So now we are at 10 nanoseconds. We've just finished that assignment, and we know that it won't be assigned again until 10 nanoseconds later, so we could just draw that all the way out. And so the question is, does this wake up again? Well, no, it's not going to wake up until 35 nanoseconds, right? It's not going to wake up until 35 nanoseconds. So what's happening is, we now got to go ahead and see, did anyone else wake up because of this event of it going low at 10 nanoseconds? No, because we're only sensitive to the positive edge of the clock and the negative edge of reset. So, when will we wake up again? When is the next event that will cause the simulator to look at process 1, 2, or 3? Well, this isn't going to happen until 35 nanoseconds, so that's out of the question. And this is going to happen at 20, so what do you know? This is the next one to be evaluated. And since it's a blocking, it happens immediately. So our question is, now that this is assigned, is there anything else to be assigned at this point? Well, actually, not yet. What's going to happen is we're going to see, did any events occur? Yes. This is a pause edge. And so what's going to happen is we're going to say pause edge clock. But we're going to realize we're still in reset. So sig out still keeps a value of 0. Okay? And so we do this again, and the process continues. So this process 1 won't wake up until 10 nanoseconds later. So we can draw that out all the way. And we kind of recognize a pattern here. And what I'm going to do here is, to kind of get this conversation going a little faster, is I'm just going to draw this out all the way. Okay. So what's going to happen is at 40 nanoseconds, I'm sorry, at 35 nanoseconds, our reset, this is activated. So what happens is reset goes, we grab the right-hand side, we see if anyone else gets assigned at 35 nanoseconds or wakes up. Nope. So then we go ahead and we assign it. And then we see, does anybody wake up because of that event? No, because we're not sensitive to the positive edge of reset, we're only sensitive to the negative edge. So what happens is this goes high. And as you can tell, reset never gets touched in our design ever again. So we can actually just draw that all the way out. So, with that said, now we're here. And now we have a comment that says at pause edge clock. So the question is, when do we activate next? Well, we activate at 40 nanoseconds because of our clock statement, right? And we activate also, check this out, at the next positive edge of the clock. This is actually an event. This is what we can use inside of our Verilog simulation environment, our behavioral code, to say, wait for the next clock so we can inject an input. So what's going to happen here is we're going to wait until this clock right here. This clock is our big event, okay? So what's going to happen is that's going to be what we're sensitive to. So we're going to go to this point, and then we can execute this statement. At the same time, we're going to invert the value of toggle. So this gets inverted first, we assign it. And then we go through and we say, okay, well, did any events occur? Yes, this event occurred and this event occurred. So we have process 2 and 3 that will be scheduled accordingly. So let's start with process 2. We say toggle goes to 1. So toggle doesn't actually go to 1 right away, right? We grab the right-hand side. So we grab the right-hand side here. Now pay close attention, because this is where people get confused. We grab the right-hand side, and this is woken up too, right? So this gets woken up because of what? It gets woken up because the clock went on a positive edge. And we are also out of reset, so we're going to go here. Is toggle high at this point? Is toggle high right here? No, it's not actually. So what happens is nothing gets evaluated. So sig out will actually stay low for yet another clock cycle because we haven't completed the assignment yet. So what will happen is we'll grab the right hand side of basically, we'll just keep the value actually because this statement never gets executed. So sig out keeps its old value. It doesn't even grab or do an assignment. So we then grab the right hand side, we then assign it. Okay, there we go. And so as you can see, toggle goes high. Now when's toggle going to be affected again? It'll actually be affected at the next clock. Okay, so we wait this goes one whole clock before it's changed again. Okay, well we know that this occurs, it changes it, and then it wakes up this line of code. And we also know that it wakes up this entire process. Okay, so we wake up this line of code, and toggle, we basically grab the right hand side, which is 0. Okay, but so we're waiting to go ahead and gather the right hand sides from all the rest of the processes and assign all the blocking statements. We come back and we look at this process now, which is also woken up. We say, is toggle set? Yes, toggle is set because we have not completed the assignment here, right? We have not completed the assignment to the right hand side. So what's going on here is this will actually take the inverted value of sig out. So sig out will actually go high here. Okay, it'll go high for one clock cycle. Okay, well, what's going to happen is we're going to invert. We're going to grab the right hand side, and the right hand side is actually 1 in this case. Okay, sorry, I got ahead of myself. So we grab the right hand side. Okay, now is there any other non-blocking assignments to be captured, or is there any blocking assignments yet remaining? No. Okay, so the question is, what's left? Well, now we just assign. We assign the right hand side. Okay, and that right hand side is going to be high until the next clock edge, and toggle will be low until the next clock edge. Okay, so that's kind of how this works, right? It's pretty simple to understand once you go line by line. And so this should kind of help you understand what you were seeing in the waveform, or what you were seeing in the class, and what I was expecting of you. So let's call it done. I think that should be good. Let's, thank you. Thank you for your time and your attention.